In this section, we'll talk about arc length and curvature. Now, one thing that we've seen in Calculus 2 is that we can compute the arc length of a curve on the plane. And we can do that with a parameterization. So recall that given a plane curve C, that is parameterized by x equals some function of t. Now, we could say f of t, but here we're just going to say x of t to keep things matched up and obvious which goes with which. And likewise, we could say y equals g of t, but here we'll just write it as y of t. Given a plane curve that is parameterized by x equals this function of t and y equals this function of t, then the arc length which is denoted with the letter s, the arc length s on the interval from a to b is given by s equals the integral from a to b of the square root of x prime of t squared plus plus y prime of t squared dt. Okay? Note that this parameterization is nothing more than a vector-valued function. Here, note, this can be written as r of t equals x of ti plus y of tj. And so this arc length is nothing more than s is equal to the integral from a to b of, well, let's see, I'd have the derivative of the components. Okay, well, that's just the derivative of r. And then I would have the components of that derivative squared, added together under a square root. Oh, well, that's just the magnitude. Right? So here, this would be the magnitude of the derivative of r. Like that. But that has a natural extension into space. After all, we proved this is true in Cal 2, but that's analogous to this. It means the same thing as this if you think of this parameterization as a vector-valued function. So we can extend this into space. S is equal to the integral from a to b of the square root of, well, if we had a vector-valued function in space, it would have three components. So taking the derivative of that would give us the derivative of x, the derivative of y, and the derivative of some z of t. And then taking the magnitude of those would give us x prime of t squared plus y prime of t squared plus z prime of t squared dt, which of course is also equal to this. But with this extension of this previously known arc length formula, now we can consider the arc length of curves in space. So for example, let's find the arc length. Find the arc length of r of t equals 2 sine of t, comma, 5t, comma, 2 cosine of t on the interval from 0 to pi. All right, well, this is how you find the arc length of any vector valued function. You're going to take the integral from the beginning to the end of the interval under consideration of the magnitude of the derivative of the position function, or the derivative of the vector valued function that you're trying to find the arc length of with respect to t. So here, if you just remember this one, doesn't matter how many components you have. You can have a 3-component, 2-component, 20-component. It wouldn't make any difference. So for this particular example, you'd have the interval from a to b, which is from 0 to pi. We're taking a magnitude, which is the square root of the sum of squares of things. Okay, so let's see here. We're going to take the square root of the sum of the squares of the derivatives, hence the r prime, of these 3 components. All right, so if I take the derivative of 2 sine of t, that'll give me 2 cosine of t, which does need to be squared. Plus, if we take the derivative of 5t right here, that'll give us just 5, which again needs to be squared, plus the derivative of 2 cosine of t, well, that'll be negative 2 sine of t. And again, that does need to be squared. Okay. Here, that needs to be simplified. Here, if we square this, this will give us the integral from 0 to pi of the square root of, well, let's see, that's going to be 4 cosine squared of t. I'll go ahead and put this along with this one because I see 2 trigonometric functions and there's probably some identity or some clever way of combining them. 4 cosine squared of t. Here, squaring a negative makes that a positive anyway, so plus 4 sine squared of t. And right away, I'm seeing the Pythagorean theorem pop out at me. Plus 5 squared, which is just 25. Okay. But of course, we know that cosine squared of t plus sine squared of t is equal to 1. So here, that's the integral from 0 to pi of the square root, forgetting my differential here, there you go, the integral from 0 to pi of the square root of, here, if I factor out a 4, that's going to be 4 times cosine squared plus sine squared of t, in other words, 4 times 1, which is 4, plus that 25 dt. So that's going to be the integral from 0 to pi of the square root of 29 dt, and now things are nice. Because, of course, here, the integral of a constant with respect to t is just that constant times t, root 29t. And we're evaluating that from 0 to pi. So that'll give us root 29 pi minus root 29 times 0, the upper minus the lower boundary. And so, obviously, that's just 0. So our result will be root 29 pi. And that's the arc length of this curve over this interval, where t goes from 0 to pi. I suppose I should say that on t in the interval from 0 to pi, right? That is, we're not keeping x or y or z in that interval. We want the parameter t in that interval. Note that as long as you remember this, you don't particularly care if it's in space or on the plane or even in dimensions beyond 3. So here, go ahead and give this a try on just the plane. Go ahead and find the arc length. And you've seen a pattern at this point. I have to give some more trig, don't I? Find the arc length of r of t equals t I plus t squared j on the interval where t is in the interval from 0 to 4. Here, we're not missing a term here. This really is just on the plane. On the plane. So don't worry about saying, okay, that's going to be plus 0k. You could, I suppose, but here, we're just considering this on the plane. All right? You might say, well, wait a minute, I don't see any trigonometry there. You will once you start taking the integral. All right, so go ahead and give this a try. This is on the plane, but it still uses this right here because this doesn't matter. It doesn't matter for this whether you have 2 components, 3, or 50. So go ahead and give that a try. Pause the video and give yourself the time you need. And once you're done, go ahead and unpause, and we can go through that together. All right, so as we see here, we want the integral from a to b of the magnitude of r prime of t. Take the magnitude and then integrate with respect to t. All right, well, that's going to be the integral from 0 to 4 of, we're going to take the square root of the sum of the squares of, okay, so we're taking the magnitude. In here you have the derivative of r. Okay, so we're going to take the derivative of these components. The first derivative is just 1, so that'll be 1 squared, plus the derivative here is going to be 2t, like that, and that'll be squared, integrated with respect to t. That makes that the integral from 0 to 4 of the square root of 1 plus 4t squared dt. And now thinking back to Cal 2, when you're integrating something that's a sum or difference of squares under a radical, that's a trig substitution. So even though trigonometry does not start off in our problem, we're going to need it to integrate that. Whenever you have the sum of squares under a square root, that's the tangent substitution. Here, you can think of that as being, okay, how do I get 1 plus 4t squared if I'm using trigonometric operations, trigonometric functions? Okay, well, I can think of an angle inside of a right triangle. It looks like I've added the square of 1 to the square of 2t. So if I call this 1 and this 2t, then completing the Pythagorean triple, that's going to be the square of this plus the square of this would give me the square of this. Okay, so I don't want the square of this. I just want how long this is. Okay, so I'll take the square root of the whole thing. So basically just the Pythagorean theorem to solve the hypotenuse. A squared plus b squared equals c squared. But since I don't, so a squared plus b squared equals c squared. Oh, but I don't want c squared, I just want c. Okay, so take the square root of the whole thing, and that's that expression. So here we have a substitution. Notice the tangent of theta would be the opposite over the adjacent. Tangent of theta is opposite over adjacent. Here I can write that over 1, or I can just leave it like that because it's the same thing. So right here, we could now substitute using 2t is equal to the tangent of theta. Well, if 2t is equal to the tangent of theta, that means t is equal to 1/2 tangent of theta, which means that our differential, dt, is going to be 1 over 2 times the derivative of tangent of theta, which is secant squared of theta, d theta. So that's going to give us, well, let's see, the square root of 1 plus 4t squared. Notice right here in our triangle, that's going to be the side, the hypotenuse over the side that's adjacent to the angle theta. Adjacent over hypotenuse would be cosine, so hypotenuse over adjacent would be the reciprocal of the cosine. That would be the secant function. So right here, square root of 1 plus 4t squared, that's secant of theta. And then here dt is 1/2 secant squared of theta. D theta, like that. And we're integrating. Now here we're integrating from 0 to 4. Right? Well, we're changing our variable. So here, we can do one of two things. We can either leave these off until the end, or probably more simply, we can simply convert them now. Because when we say from 0 to 4, what we mean is t goes from 0 up to t is equal to 4. Okay, so we can say, hey, if t is equal to 0 right here, then we can solve for theta. And if t is equal to 4 right here, again, we can solve for theta. So that really is up to you. If you want to change your variables straight up and rewrite your boundaries, you go ahead and do that. Otherwise, just go ahead and take the antiderivative and then back substitute at the end. it really doesn't make much of a difference. Here, I can take the 1/2 and factor it out. I suppose I'll go ahead and just do it without the boundaries and then go back at the end. All right? So here, I guess I shouldn't write equals because this is the definite integral. This is an indefinite integral, so obviously they're not equal to each other. That's going to be a number. That'll be a function. So I won't say equals, but let's just say I want this. I want that. Okay, so that's going to be 1/2 times the integral of secant cubed of theta d theta. And now that's another result from Cal 2. That's the one where we perform integration by parts. So here we can split this as 1/2 the integral of, we can write this as, oh, I guess I could have just left it this way, secant of theta times secant squared of theta d theta. In this case, we can go ahead and perform a integration by parts decomposition here, where we're going to take this one and call it u. And I'll take all of this stuff and call it my dv. All right? So if u is equal to the secant of theta, then du is the derivative of the secant of theta, which is secant of theta tangent of theta. And then if dv is secant squared of theta, all right, let me put it over here, dv equals secant squared of theta, then v is just the integral of the secant squared of theta, which is the tangent of theta. Okay, so here that's going to give us that 1/2 on the outside. The integral of u dv is equal to u times v. Okay, so that'll be secant of theta times dv. Oh, sorry, that's u times v. So secant of theta times tangent of theta. Here's my u and my v. Minus the integral of v times du. So here's v and du. So that'll be secant of theta times tangent of theta times another tangent of theta. So secant of theta tangent squared of theta. D theta. Like that. Okay, so now we're going to convert this one. There's a Pythagorean identity that tells us that the tangent squared of theta is the same as the secant squared of theta minus 1. So this is 1/2 times secant of theta tangent of theta minus the integral of secant of theta times secant squared of theta minus 1 d theta. Okay. So now we can write that as 1/2 times the secant of theta tangent of theta minus the integral of secant cubed of theta and then minus a minus, so that could be plus secant of theta, which I guess I'll write as its own integral. So that would be secant of theta tangent of theta minus, and I have this integral right here, secant cubed, and then I have minus another minus, so I'll make that a plus secant of theta. Okay. All right, so now I guess we'll continue on to another page here. Look where we are. We have that the integral, I'll just rewrite that back over here. We have that the integral of, let's see, 1/2 secant cubed of theta d theta. That's what we wanted in the first place. We wanted this one, which is really just 1/2 the integral of secant cubed of theta d theta. That's going to equal to, and I'm going to go ahead and cut out some of this middle stuff because, you know, that equals that, and that equals this, and that equals this, and that equals this. We end up with this expression here, which, incidentally, I guess I'll make one more line here. That's 1/2 secant of theta tangent of theta. Here we know the integral of the secant of theta. That's the natural log, so plus, yeah, the natural log of the absolute value of the secant of theta plus the tangent of theta, minus the integral of the secant cubed of theta d theta. So that gives us that 1/2 this integral is equal to 1/2 times all of this stuff. And I've gone ahead and distributed my 1/2. That 1/2 applied to this whole thing, so I've gone ahead and distributed there, there, and there. But now we're done. Because notice, this answer is the same as the original question, which means they're like terms we can combine. If we write this as 1/2 the integral of the secant cubed of theta d theta, add that to both sides, secant cubed of theta d theta, that's going to equal to, well, add those together, that's 1/2 plus 1/2, that's 1 whole. The integral of the secant cubed of theta d theta is equal to 1/2 the secant of theta tangent of theta plus 1/2 the natural log of the absolute value of the secant of theta plus the tangent of theta. Which normally we would say plus c, but we're about to back substitute and plug in some numbers. So I suppose I can say plus c for now. So what that means is, now remember, we didn't want integral secant cubed of theta. We wanted half of that. We wanted 1/2 integral. Okay, so take this answer and cut everything in half. So that means that 1/2 the integral of secant cubed of theta d theta, which is what we wanted, we'll just split all this in half. So that's 1/4 secant of theta, tangent of theta, plus 1/4 the natural log of the absolute value of the secant of theta plus tangent of theta, plus, and again, if you take a constant and divide it by something, it's still just a constant. Like that. So now at this point, we are going to now have to back substitute so we can plug in our original boundaries, our 0 and our 4. That does kind of make the case for changing our boundaries at the beginning, right? If we had changed our boundaries from 0 to 4 to whatever is necessary for theta, then we wouldn't need to back substitute right now. All right, so that kind of does make the case for, okay, maybe we should have changed those from the beginning. But you don't need to, because you can always back substitute. After all, here, that's going to be 1/4. We want the secant of theta. Oh, secant of theta is what? The hypotenuse over the adjacent? So that's just going to be the square root of 1 plus 4t squared times the tangent of theta, which is what? The opposite over the adjacent. So that's just going to be 2t over 1, or just 2t. So that's going to be the 1/4 secant of theta tangent of theta plus 1/4 the natural log of the absolute value of, and those are the same except with a plus in between. So square root of 1 plus 4t squared plus 2t plus our constant of integration. So now that we're back in terms of t, that means that our integral from 0 to 4 of the square root of 1 plus 4t squared, turns out that was all of this stuff, 1/4 square root of 1 plus 4t squared times 2t. I guess I can just write that as t over 2, right? 2 over 4 is the same as 1 over 2. Put your t on top. Plus 1/4 the natural log of the absolute value of the square root of 1 plus 4t squared plus 2t. And I don't need my constant of integration because I'm about to plug in my boundaries from 0 up to 4. So again, all I've done here is I've combined these 2t divided by 4, that's t over 2, left that alone, plus leave the 1/4, natural log, leave all this alone. We don't need a constant of integration because we're about to plug in our boundaries, and that constant would cancel out anyway. So finally, when we plug in 4, that's going to be what? 4 over 2. That's 2 times the square root of 4 squared is 16 times 4 more is 64 plus 1 more is 65 plus 1/4 the natural log of the absolute value of, let's see, that's 65. That's the same number as that one. Square root of 65 plus, let's see, 2 times 4 would give us 8. Minus, and let's see, if we plug in zeros, what do we get? That's going to be 0 times anything. All right, well, that's 0. Okay. Plus, here we'd have 0 times 2 is 0. Here 0 times 4 is 0, plus 1 is 1. So this is 0 plus 1, which is 1. And then we'd have the natural log of that 1, which again is 0. Okay, so it looks like that part's gone. We don't worry about that. And in the end, we get our result, which is 2 root 65 plus 1/4 the natural log of, here we don't need the absolute values because those are both positive numbers anyway. The natural log of root 65 plus 8, which, okay, may not be the nicest number, but it is our result. A couple of things to note here. One, just because something's in the plane does not make it easy. Here, this was in space and worked out relatively nicely. This was in the plane and required quite a bit of work. What makes it difficult or simple is not the number of dimensions that it's in, but rather the particular integration that you have to complete. The other thing to note here is that, well, we're in Cal 3 now. That doesn't mean all the material from Cal 1 and Cal 2 have gone away. Here, this is this problem I picked in particular because it uses several of the methods that we see in Cal 2. Namely, it uses integration by parts, it uses trigonometric substitutions, it uses iterated substitutions here, and it uses some trigonometric integrations here, where you take the integral of the secant function. That's the natural log of secant theta plus tangent theta, right? It also could use change of variables, although in this case we didn't bother changing the boundaries, but I mentioned twice that it could be. And finally, back substitution, which can involve trigonometric expressions or can involve really anything else whenever you use substitution. So this is meant to be a reminder of the elaborate integration techniques that you learn in Cal 2, and also a reminder that none of those should be forgotten, because while they are not the central part of this course, they are still mechanical techniques that you do need to have fluency in for some of this stuff to be accessible to you. Right. Now, once you have defined the concept of an arc length in general number of dimensions, whether it be on the plane, in space, or otherwise, we can define the following parameterization. We've seen that we can parameterize things based off of an angle, theta. We can parameterize things based off of the amount of time elapsed from some starting position, from t equals to 0. In Cal 2, we've even seen a few examples where you can parameterize things based off of their slope. As the slope changes, we parameterize based off that slope. Here, we're going to see the arc length parameter. We're going to see what it's like to parameterize things not based off of a position or a time or an angle, but an arc length. So let r of t define a smooth, remember, smooth means that the derivative, the components have derivatives that are continuous. Let r of t define a smooth curve on a closed interval a to b. Okay? And let t be some number in that interval, including possibly either endpoint. Okay. Then s of t, notice it's a function, and we're using s, the same symbol that we use for arc length. That is not a coincidence. That's telling what's about to happen. S of t is equal to the integral from a to t. So notice not from a to b necessarily, but from a to some point t, some value t in here, of the magnitude of r prime of u du. You might wonder why u, because we're already using t as that upper bound, so it would be confusing to use t for more than one thing. Here, based off of how we've defined the arc length, you could also write this as the integral from a to t of, and here we're assuming this is in space, however this could be in the plane or in higher dimensions. But in any event, for space, which is what we're looking at primarily here, it's the integral from a to t of, well, this, namely the derivative of each component squared and then added together under a square root. This is called the arc length parameter. So as an example, let's go and find the arc length All right, let's find the arc length function s of t for r of t equals 3 minus 3t, comma 4t, on the interval from 0 to 1. Oh, and I guess that's not the end of the question. So find the arc length function s of t for r of t equals 3 minus 3t, comma 4t on the interval from 0 to 1. Then we're going to write r as a function of s, as a function of the arc length. All right, so let's go ahead and do that. So we're going to start with, let's take r prime of t. We want r prime's magnitude, so let's start by finding r prime. That's going to be given by, let's see, negative 3, comma 4, okay, taking the derivative of each component. And then we're going to want the magnitude. So the magnitude of r prime of t is equal to the square root of the sum of the squares of negative 3 and positive 4. In other words, it's equal to the square root of 25, which is just 5. So that means that our arc length function s of t is defined as the integral from the beginning of the interval up to some value t, where t is somewhere between 0 and 1. So from 0 to t of that magnitude of that derivative. So just like that, with respect to t. I guess I should say with respect to u, right? There you go, just like that. And so here, if I integrate 5 with respect to u, I get 5u. And that's from 0 up to t. Okay, well, if you plug in t right there, that's 5t. If you plug in 0 right there, that's just 0. 5t, like that. Okay, so there is our arc length function. Note that what this is telling you This is telling you the arc length of this vector valued function. If t is equal to 0, right here, then your arc length is 0. Because, of course, from here you're saying, okay, well, you're going from 0 to 0. You didn't go anywhere, so your arc length is 0. Okay, what if you're going from 0 all the way to 1? Okay, well, then t is equal to 1. And if you have t is equal to 1, the integral from 0 to 1, that's going to give you 5 right here. So basically, as long as t is equal to whatever upper bound, that gives you the arc length. You want to find the arc length of this vector valued function from 0 to 0.73. Okay, well, 0.73 times 5. That's your arc length. This tells you, hey, you tell me how far along the interval you got, and I'll tell you what your arc length is. Just plugging it in right here. So now the second half, right? Here, actually the name itself tells you what's going on. It's the arc length function. You tell me what value of t you have, and I'll tell you how far I'll tell you what the arc length is from 0 to that value of t. Now the second one says now we're going to write r as a function of s. Well, here we have that s, the arc length, is equal to 5 times t. Since s, and here we could say s of t, but that's going to make things a little confusing. S of t equals 5t, especially with my handwriting. So I'm just going to say s equals 5t. Then you could also say t is equal to s over 5. Ooh, that is going to be very bad with my handwriting, but s over 5, like that. So now with a simple substitution, we get that instead of r of t, we can write this as r of s, which is equal to, well, here we're replacing t with s over 5. So that'll be 3 minus 3 times s over 5. Okay, so that'll be 3 minus 3/5 s, comma, and then you're taking s over 5, replacing t with that, and then times 4, so that'll be 4 over 5s. 4 over 5s. Note that since over here in the original parameterization with respect to t ran from 0 to 1, then since t is 1/5 of s, or since s is 5 times t, that means that if t is running from 0 to 1, then that means for s in between 0 and 5. Because, of course, here, when t is equal to 0, s is equal to 0 times 5. Well, that's 0. And when t is equal to 1, s is equal to 5 times 1, which is 5. All right. Again, note what you're doing. You've given this curve a parameterization not based on time, but based on arc length. As a quick illustration, if we were to draw this curve, we'd have something like this. This is a plane curve, so we don't have to draw anything in space. Okay. Now, for values of t, when t is equal to 0, this is what, 3 comma 0? That's when t is equal to 0. When t is equal to 1, I get 0 comma 4. And everything in between. Note these are both linear, so the whole thing will be just a straight line. It's not even a line, it's just a line segment from here up to here. Okay. Now normally, with this parameterization, I could say, okay, where am I on this curve? Well, how much time has passed? Oh, half a second has passed. Oh, okay, then you're right here. Oh, I'm sorry, I meant 1/4 of a second has passed. Oh, right here. I mean 0.99 seconds have passed. Oh, I'm way up here. With the arc length parameter, now what I'm asking for is not how much time has passed, but how big of arc length do I want? Oh, well, arc length can go from 0 to 5. Okay, well, I want the full arc length of 5. Okay, well then plug in a 5 right there and a 5 right there. Well, that'll give you 0 comma 4. So if you go all the way to here, you'll have the full arc length. Oh, no, I don't want a full arc length. I only want an arc length of 3. Okay, so plug in a 3 right there. 3 minus 9/5, comma, 12/5. Oh, that'll give me the point where if I go from here to there, I'll have arc length of 3. So you tell me what arc length you want, and this will tell you how far you need to go to get that much arc length. You're literally parameterizing based off of arc length instead of you're parameterizing based off of how much arc length is passed rather than how much time is passed. One thing to note about the arc length parameter is that it's rather useful if you notice the following. Right here, we found that here was our r prime of t, and here was our r prime of s. Okay? Notice what happens if you take the magnitude of the derivative of this one. Now, we found the magnitude of the derivative of r of t. We found that to be 5. Okay? Notice what happens if you take the magnitude of the derivative of r prime of s. Well, let's see. That's going to be the square root of the sum of the squares of the derivative of the components of r of s. Okay, well, there's r of s. And if I take the derivatives, well, that goes to 0, and that's just minus 3/5, and that'll be positive 4/5. Minus 3/5 and positive 4/5. So that'll give us the square root of, what would that be? 9 over 25 plus 16 over 25, which is just the square root of 25 over 25. Or in other words, it's the number 1. That's not a coincidence for this particular parameterization. It turns out that if you take the magnitude of r prime of s, you get 1 in general. This is always true. Okay, so what? Well, then we can write our arc length formula a slightly different way. Here, s is equal to the integral from a to b of the magnitude of r prime of t dt. But no one ever said I had to parameterize with respect to time. This is just a parameter. Okay, so the arc length parameter is a perfectly good parameter. I can write this as arc length is equal to the integral from a to b of the magnitude of r prime of, and instead of using the parameter t, I'll use the time, instead of using the time parameter, I'll use the arc length parameter, ds. Oh, but this is always equal to 1, generally speaking. Okay, so then that's got to be the integral from a to b of 1 ds, which is the integral from a to b of just ds. Okay, but what's the integral of the differential with respect to s? That's just going to be s evaluated from a up to b. Oh, but that's just going to be b minus a. But what is that? That's the length of the interval. So here, as long as you've parameterized in terms of the arc length, then we can find the arc length by simply taking the boundaries and subtracting them. Or in other words, finding the length of the interval over which you're integrating. That simplifies greatly what's an otherwise unpleasant result. All right. So now this brings us to the other part of this section. We define the arc length and the arc length parameter and show one of the nice benefits of parameterizing with respect to arc length. Incidentally, keep this in mind. We'll be using this later. But for now, let's go ahead and define curvature. Well, definition. When I say later, I mean in a coming chapter. So a definition. Let's begin with a vector-valued function that has been parameterized using this arc length parameter. So let R of S define a curve, and this can either be in the plane or in space, it won't matter, with S as the arc length parameter. Then K, which is defined as the derivative of the unit tangent vector with respect to the arc length, which can also be written as just the magnitude of T prime of S, that's just an alternate notation, is called the curvature. Of the curve. The curvature of the curve. It quantifies how curvy something is, yeah? One way you can think of it is note can be thought of as how curvy something is, right? How quickly or sharply something turns. And another thing to note is that computing K by definition is this. And it's a massive pain because you first would have to find the arc length parameter. So you are rarely given something like R of S. Usually you'd have R of T. You'd have to find the arc length parameter to reparameterize it, basically doing the problem that we had up here. The problem that we had back over here, which might not work out quite so nicely as this one. And then, once you'd have that reparameterization, then you'd have to find the unit tangent vector, and then you'd have to take the derivative of that unit tangent vector and find its magnitude, which, as we saw in a previous section, that was what was required to find the unit normal vector. Principal unit normal vector, that was the denominator of the principal unit normal vector. And, well, is it doable? Absolutely. Is it pleasant? No, not at all. So doing this by definition is a pain. Thankfully, we have some theorems that allow this to be made quite a bit more accessible. So here, let's just jump. Let's not even try to compute one of these manually. Can you? I have every confidence that you can. It's just derivatives in algebra. Should you? No. Why not? Because I don't want to do it either. So, theorem. I wouldn't ask you to do anything that I wouldn't do, and, well, frankly, I wouldn't do that. All right, so theorem, let's talk about curvature. Let R of T define a curve by any parameter. It doesn't have to be the arc length parameter. It can be the typical time parameter or an angle parameter, or if you want, it could be this one. Let R of T define a curve with any parameter T. If you want it to be the arc length, it can, or any other is fine. Any parameter T. Okay. Then, the curvature K is given by the absolute value of T prime of T the absolute value, the magnitude of t prime of t over the magnitude of r prime of t, which is a little better. Obviously, you don't have to compute the arc length parameter, so that is slightly more accessible. But that can be made even more accessible. It's equal to r prime of t crossed with r double prime of t. So now no need to normalize, no need to divide by the magnitudes of anything. Just find r prime, r double prime. Those are all usually pretty easy to find. Take the cross product and then divide by the cube of the magnitude of r prime of t. Like that. Here, the proof. So here there's actually two equations, right? That's that first equation and then that second equation. The proof of number one. All right, well, by definition, k is equal to the magnitude of the derivative of t with respect to the arc length parameter, which is equal to the derivative of t with respect to the time parameter divided by the derivative of the, that should be a t there, divided by the derivative of the arc length with respect to the time parameter. Okay, that's just the chain rule, like that. But now the magnitude of this quotient is the quotient of the magnitudes. So here that's going to be the magnitude of dt dt, like this, divided by the magnitude of ds dt, like this. But of course, this is just the derivative of the unit tangent vector with respect to time. Or in other words, it's the typical t prime of t that we saw in the previous sections that involved unit tangent and unit normal vectors. And of course, we're taking the magnitude of that one over. Here, this is just s prime of t. Like this. But since s of t is, by definition, the integral from a to t of the magnitude of r prime of t dt, then if I take the derivative of s, which is what I have right here, then s prime of t is equal to the derivative with respect to t of the integral from a to t of the magnitude of r prime of t dt. Oops, my dt should be on the outside, but yes, dt. But by the second fundamental theorem of calculus, the derivative with respect to t of the integral with respect to t, ooh, that's bad, very bad notation. I should not be using t twice, should I? Here, we can use a different value here. Let's just say u, I believe is what we did before. There we go. The integral from a to t of the magnitude of r prime of u du, that's our definition of the arc length function. Then taking the derivative of the arc length function, s prime, like what we have over here, is equal to the derivative with respect to t of the integral from a to t of the magnitude of r prime of u du. But then by the fundamental theorem of calculus, the derivative with respect to t of the accumulation function of this integrand is just that integrand with that upper bound evaluated in place of the argument. That means s prime of t is just equal to that magnitude. Like that. So the magnitude of this is the magnitude of this. Oh, so it's the magnitude of the magnitude. Whatever, it's just the magnitude. That means we get that the magnitude of t prime of t over the magnitude of s prime of t is nothing more than the magnitude of t prime of t over, if this is that, then that's the magnitude of this one right here. Oh, but that's already a magnitude. So what's the magnitude of a magnitude? That's like saying the absolute value of an absolute value. It's the same thing. So here that's the magnitude of r prime of t, which is that first inequality. Oh, sorry, which is that first equation. So this confirms part 1. Part 2 is omitted due to extreme length. Expressing this one in terms of this is extremely long to do formally. In your textbook, they have a sketch of a proof, meaning, oh yeah, notice this, and you can kind of see that if you squint, it looks like this. That is not at all a formal argument, and that doesn't it doesn't really prove this result. So instead, we'll just we're going to say this proof is kind of too advanced for us right now. Is it doable? It kind of is, but it's a lot more than what we're really willing or ready to do. So here I'll say part number 2 is omitted due to, let's say, length. It is a very long argument to formally prove this. And, well, instead, we'll just prove the first one and say the second one is, it's out there. You can confirm it if you like, but it's not something we're going to take up more time with on right here. Instead, what we'll do is we'll look at some examples. All right, so let's go and find the curvature. Of, let's see here. Let's take r of t is equal to 4 sine of t minus 4t cosine of t. That's the first component. The second component will be 4 cosine of t plus 4t sine of t. And then the third component will be 3 halves t squared. So we're going to find the curvature of this. Of course, we can do this by definition, but, well, I think we may exploit one of our proofs, one of our theorems instead. So, in fact, here we'll exploit this proof here, or this first conclusion here, and we'll simply compute the magnitude of t prime of t over the magnitude of r prime of t. All right, so let's go and take a look. So first, let's compute r prime of t. Okay, well, that's not too bad. That's going to be 4 times the cosine of t. Here we're going to need to use the product rule, so that'll be minus, let's see, the derivative of the first times the second. So that'll be minus 4 cosine of t. And then the derivative of the second times the first. So that'll be derivative of cosine of t is negative sine of t, and minus and minus will make that plus 4t sine of t. All right, so there's the derivative of the first component, and then we'll take the derivative of the second component. 4 cosine of t has a derivative that's negative 4 times the sine of t, plus, and then we have to use the product rule here as well. The derivative of the first part times the second, that'll be 4 sine of t, plus the derivative of the second times the first, so 4t cosine of t. And then the derivative of the third component, take your 2, bring it down, subtract 1 from the power. So that'll give us 3t. Just like that. All right, now let's go ahead and compute the magnitude of r prime of t. And that's going to be the square root of the sum of the squares of these components. All right, so let's go ahead and square these, and oh, that's going to look unpleasant, isn't it? Oh, actually, not so bad. Those just go away. 4 cosine of t minus 4 cosine of t. And here 4 sine of t minus 4 sine of t. I sure do enjoy living in math book land where the problems are set up so that things work out not terribly unpleasantly. This is just one of the examples out of the out of our exercises. So here we're just taking the this one and squaring it, this one and squaring it. Okay, that's much nicer. So if I square this, that's going to be 16t squared times the sine squared of t. Plus, if I square this one, that'll also be 16t squared times the cosine of t. Okay, so those have a common 16t squared, which I'll factor out, and I'll just be left with sine squared of t plus cosine squared of t. Okay. Plus, and then we'll square that third component. So it'll give us 9t squared. Since that's just the number 1, really this gives us 16t squared. Here, let's just say that's the number 1. That'll give us 16t squared plus 9t squared. No, plus 9t squared. That'll be 25t squared. And then we can actually take the square root of all that. That'll just be 5t. So that one's pretty nice. All right, so now we're going to put these together to find t of t. We're going to find the unit tangent vector, which is simply r prime of t over the magnitude of r prime of t. In other words, we're dividing these two things, this one by this one. So that's going to be 4t sine of t over 5t. Well, the t's divide away, and that just leaves me 4 sine of t over 5, comma. Same thing with this one. The t's divide away, and we're left with 4 over 5 cosine of t. And then here, 3t over 5t, the t's again divide away, and we're left with 3 over 5. Okay, so that is t, the unit tangent vector. Now remember, our formula here is we want to find our denominator is the magnitude of r prime. Okay, we actually already have that. Magnitude of r prime is 5t. And then we want the magnitude of the derivative of the unit tangent vector. Okay, so let's take the derivative of this one, find the magnitude, and then we're done. So here that'll be t prime of t. That's just the derivative of all of these components. Thankfully, the derivative of vectors is done component-wise. So here the derivative of 4/5 sine of t is going to be 4/5 the cosine of t. Comma, the derivative of 4/5 cosine of t is negative 4/5 times the sine of t. And the derivative of 3/5 is 0. Derivative of any constant is 0. So that means that the magnitude of t prime of t is equal to the square root of the sum of the squares of these components. So that'll be 4 cosine of t over 5 squared plus negative 4 sine of t over 5 squared plus 0 squared. So here that'll give us the square root of, let's see here. That'll be the square root of 16 over 25 cosine squared of t. 16 over 25 cosine squared of t. Negative squared, that'll give me a positive. That's also 16 over 25, so let me factor that out. And if I factor 16 over 25 from both of them, I'm left with cosine squared of t plus sine squared of t. Plus 0. And that'll give us the square root of 16 over 25, which is just 4/5. So there we see the magnitude of t prime of t. So then from our theorem, we get that k is equal to the magnitude of t prime of t divided by the magnitude of r prime of t, which is 4/5 over, that one was 5t. Or in other words, 4/5 divided by 5t, that'll give us 4/5 times 1 over 5t, that'll give us 4 over 25t. And there's our curvature. Note that that is variable and based off of t. Here, as t gets larger, the entire thing gets smaller. So it looks like as t grows, your curvature shrinks. So that is our result. And that is still a bit of a lengthy computation, but nowhere near as much as you would have if you started from scratch by the definition. Oftentimes I'll start with the simple one and I'll ask you to do one, and it turns out to be the complicated one. Here, let me give you the simple one. So here, let me give you the one that doesn't use trigonometry. Right? Go ahead and give this a try. This should not be terribly difficult, and if you get a nice simple answer, well, that's what you're supposed to get. Find the curvature of r of s. Notice this one actually is given to you as a arc length parameter. R of s is equal to 3 plus s, comma, 1. So go ahead and give this a try, and once you're ready, we'll go through it together. All right, now, this may look like it would be different because here this one is parameterized with respect to the arc length parameter. But in reality, we saw that our theorem here said r of t defines a curve with any parameter. So here, even if it's r of s, r of t, r of theta, r of an angle, slope, it makes no difference. This still applies. So here we're going to say k is equal to, and I'll just go ahead and use the same one. It's going to equal to the magnitude of t prime of t over the magnitude of r prime of t. Okay? Okay. So let's go ahead and find, actually, I suppose that should be of s, since that's the parameter given. Not that it'll make any difference. So here we can say, all right, let's find r prime of s. Well, that's just going to be 3, not even 3, that's going to be 0 plus 1. Okay, so that's 1, comma 0. Okay. Next we need the magnitude of r prime of s. Oh, well, that's just obviously the number 1, yeah? So it's going to be the square root of 1 squared plus 0 squared. That's got to be 1. Okay. So now, just like above, we can take t to be given by r prime over the close that one off, magnitude of r prime. So right here, we can put this together, and we get t of s is equal to r prime of s over the magnitude of r prime of s, which is going to be 1 comma 0 divided by 1. Or in other words, 1 comma 0. Since dividing by 1 doesn't change any of the components of our vector. Okay. So now we're going to want t prime of s. All right, we're going to want the t prime of s and then take the magnitude. Okay, well, if that's t of s right there, 1 comma 0, t prime of s would be, well, both of those are constants. So the derivative of constants is just 0. Oh, that's the 0 vector. And then I want the magnitude of the 0 vector, which, if there's any justice in the world, it's got to be 0, doesn't it? Yeah, clearly that's 0. So over here, that means that our curvature is 0 over, here r prime of s has a magnitude of 1, 0 over 1, which is 0. You might say, well, how can that be? It's constant. This is linear. After all, each of the components are linear, which means that this curve is a straight line. What would you define as the curvature of a straight line? How much curve does a straight line have? None. It has no curvature. So here, that makes sense given the nature of this, the fact that it's linear. I said that would be nice, albeit a little anticlimactic. Now, the next thing we're going to look at, let's talk about curvature, not in a time parameter, not in an arc length parameter. Let's go back and discuss curvature on just a regular plane, on the xy plane. Let's talk about this in rectangular coordinates, because after all, this is one of the first things we've seen that was not first defined on a rectangular coordinate system. Usually arc length, derivatives, integrals, all that was defined on the xy plane, and then we extended into the plane or into different parameterizations. Here, curvature, well, we haven't seen it in rectangular coordinates at all. So here we have a theorem. Let C be the graph of a twice differentiable twice differentiable function, perhaps a site for sore eyes, the traditional y equals f of x. After different kinds of parameterizations, you might have missed this guy. Y equals f of x. The curvature at the point x comma y is k equals the absolute value of the second derivative of y over 1 plus y prime squared, the square is only on the prime here, raised to the 3/2 power. The proof of this one is it's a little strange. It's straightforward, but somewhat ingenious. Here you would think, okay, well, I've got something in the plane, so I must be dealing with it in the plane. Well, it turns out that the proof requires us to extend this into space. This is actually something that we will see more and more throughout this course. Sometimes things that are difficult or inaccessible in a certain dimension are made simpler if you extend into a higher dimension. Sometimes it's easier to deal with things on the plane if you pretend that the plane happens to be sitting in space. In later sections, we take that to an even greater extreme, where things that are in space are made simpler if we think of space as lying in some fourth or fifth dimensional space, I guess, for lack of a better word. Maybe fourth dimensional system would be better. So here, proof. Let's let C be given by a vector valued function of x. Right? Here we want things to depend on x, not on some other parameter. And here we're going to give that as being, the first component is x. The second component is f of x. We want it to be that y value, and y equals f of x. You say, well, okay, but this is on the plane. How do you get a third component? Well, we just pretend we're on the xy plane of the xyz coordinate system. Basically, you're saying this. Yes, I know I'm on the plane. But let's pretend that the plane that we're talking about happens to be this plane right here, the one that is one of the traces on the xyz coordinate system. Okay, fair enough. There's nothing that prevents us from saying, oh yeah, the plane that we're used to happens to be this plane, but it also was sitting in space. We just never bothered to mention it. That's sort of the ingenious part. We don't consider this as a plane. We consider it as just a special little corner of space. Okay, so now we're going to go ahead and use this second unproven part of our theorem here. The curvature is equal to this. We proved this and have used this a few times. We're going to use this one this time. All right. All right, well, in order to use that, so in fact, let me write this over here so I don't have to keep flipping back and forth. Recall that, let's see, K is equal to the magnitude of R prime of, and remember, this can be any parameter. So yes, it's R of t with the way it was written here, but the curvature can be of any parameter. And here we're using the parameter x. Okay, so that's fine. That'll be R prime of x crossed with R double prime of x. Okay, we're just taking that numerator here and replacing the t's with x's. And then we're dividing the whole thing by the magnitude of the derivative raised to the third power. So dividing everything by the magnitude of R prime. And that magnitude is raised to the third power. So it looks like we're going to want to find the first and second derivatives. R prime of t, R prime of x, there we go, is going to be, well, the derivative with respect to t, I've gotten used to saying t, the derivative with respect to x of x is just 1. The derivative with respect to x of f of x is df dx, or I think I'll save a little space by using Newtonian notation, f prime of x. And the derivative of 0 is, well, it's 0. Okay. Let's go and take the second derivative, r double prime of x, and that's going to be the derivative of 1, well, that's 0, and the derivative of f prime, well, that's f double prime. The derivative of the derivative is the second derivative, and again, the derivative of 0 continues to be 0. It hasn't gotten tired of being 0. All right, now, from here, I can go ahead and compute the magnitude of r prime. All right, I have r prime. Let's find its magnitude. So let's see. The magnitude of r prime of x is going to equal to the square root of, well, let's see, we're going to take that 1 and we're going to square it, plus we're going to take that f prime of x and we're going to square it, like that. Okay. All right, so now you can go ahead and cube that whole thing. Well, let's just leave that there for now. We'll cube it at the end. Now we want to find the cross product of these two. Okay, well, let's go ahead and do that. Here, if I take I, j, k, I, j, k, let's see, I'm taking the cross product of r prime and r double prime. So let me write r prime first. That's going to be 1 f prime of x 0, 1 f prime of x 0, and then r double prime is going to be 0 f double prime 0, 0 f double prime 0. With all these zeros around, this should be pretty simple. This will be, well, that's 0i plus, well, looks like that's 0j plus, that's 1 f double prime k. Minus, that looks like that's 0i, and that's 0j, and that one's 0k. Well, that was simple. There's only one component. It's going to be f triple prime of xk. Okay, so then here we get that r prime of x crossed with r double prime of x is nothing more than 0, 0, f double prime of x. Well, I want the magnitude of that, though. Okay, so then that implies that the magnitude of r prime of x crossed with r double prime of x is going to equal to the square root of, well, that'll be 0 squared plus 0 squared plus f double prime of x squared. Well, since these are both 0, we can just ignore those. And that's going to be the square root of f double prime squared. Well, when you take the square root of a square, you get the absolute value of what's inside. So here that's going to be the absolute value of f double prime of x. So now we can put that all together. Here, k is equal to the magnitude of the cross products. Okay, well, we found that that's f double prime of x. Oh, but we took the square and then took the square root. So that gives us the absolute value of f double prime of x over. And now we're going to take r prime of x. We're going to take its magnitude, which we found to be this. Okay, so that's going to be 1 squared, that's 1, plus f prime squared. And then that's to the 1/2 power, because it's got a square root on it, so that's 1/2 power. But then it's being cubed. So 1/2 power, but then cubed. Oh, that gives us 3/2 power. Oh, but remember, f of x is equal to y. So here, when we say f double prime of x, we can just say that's y double prime. And here, when we say f prime of x, we can just say y prime. So that'll be 1 plus y prime squared raised to the 3/2 power, which is exactly what we had before. So that confirms our result. This actually makes for a reasonably nice set of problems. For example, let's find the curvature of y equals e to the power 3x. And we'll go and do that at the point 0, 1. When x is equal to 0, e to the 0 is equal to 1. Yeah. So we're going to take the curvature of y equals e to the 3x at the point 0, 1. All right, so from over here, we see we're going to need both derivatives. We're going to need y prime and we're going to need y single prime. So let's find what those are. We know y is equal to e to the 3x, which means y prime, well, that's going to be 3e to the 3x. And y double prime is going to equal to triple that. So that'll be 9e to the 3x. Like this. But of course, we don't want those arbitrarily. We want them specifically at 1, 0. At 0, 1. So here we can evaluate that at x equal to 0. So that'll give us 3e to the 0, which is 3. And here y double prime evaluated where x is equal to 0. That'll be 9e to the 0, which is just 9. So take the first derivative, take the second derivative, evaluate it at the point that you're trying to find the curvature at. So here, x is equal to 0. There's nowhere to plug in your y's. And now we have all of these, which we can now fit together this way. So that curvature is given by, and I'm just going to rewrite this, the absolute value of y double prime over 1 plus y prime squared, all raised to the 3/2 power. All right, well, we have y double prime at this point is equal to 9. I'll put it in absolute values just for show, but obviously the absolute value of 9 is just 9. Over, here we're going to take 1 plus 3 squared. After all, 3 is our y prime, so that's 1 plus y prime squared raised to the 3/2 power. Here the absolute value of 9 is just 9. Here 3 squared is 9 plus 1 is 10 raised to the 3/2 power, which is 9 over 10 root 10. Like that. So that's our curvature. Here we can even rationalize this. Let's go ahead and multiply top and bottom by root 10. And this will give us 9 root 10 over, that's root of 100, which is 10, times that other 10, which is 100. So that is, that's usually the way the book writes these results. They almost always rationalize anything. They never leave radicals in the denominator. So here, the curvature of y e to the 3x at 0, 1 is equal to 9 root 10 over 100. Now, you might be asking, what is curvature? Well, earlier on we said it's equal to, well, no, not an equation, but what is it? Well, earlier you said it was about how much something curves. Well, yeah, but what does that mean exactly? So here, this is not at all a precise statement, but we're going to give a geometric interpretation of what this number really means. Note this is by no means a precise statement, but it does give a nice illustration as to what these numbers quantify. So here we have a curve, y equals e to the 3x. So I could graph that, and I'm not going to graph that precisely, but just more or less, I know what exponential curves look like. It'll look something like this. Okay, and then what I went ahead and did is I found the curvature specifically at the point 0, 1. So that would be my point 0, 1 right there. Now, here you can compute a tangent line, right? You can do that by taking the first derivative, plugging in the point, finding the slope, and then using that point and that slope to create a line. All right, so we have a tangent line, which we could have found way back in Cal 1. Or maybe Cal 2, right? Because, no, you learned to take the derivative of e to the x in Cal 1, I believe. In any event, either Cal 1 or maybe at the very beginning of Cal 2. Okay, so there we go. We can find the line that's tangent to the curve. There exists some circle that has this line as its tangent. That circle will have a radius. K is the reciprocal of that radius. Here, there is some circle who will have the same tangent at this point as this curve. So there's some circle out there somewhere that has the exact same tangent line at that point as this curve does. This radius of this circle is the reciprocal of the curvature. Or you can say curvature is the reciprocal of the radius. Either one of those is fine. Notice that because of the reciprocal nature of this, you can say, again, r is equal to 1 over k, or you can say k is equal to 1 over r. Either of those is fine. The bigger curvature you have, the smaller radius you have. The bigger, smaller, I've gotten myself confused. The smaller curvature you have, the bigger radius you have. The bigger curvature you have, the smaller radius you have. So what that means is something that's got a lot of curvature, something that's very, very sharp. Here, K would be very high. Well, then that means that the 1 over r is very high, which means that the reciprocal must be very low. So r is very small. Oh, okay, well, that's because this is so tight that the circle that has the, let's say I'm looking for the tangent line right there, the circle that has that tangent line must be very, very small. Well, of course, because that's such a tight little fit in there. On the other hand, if you have something that's got very low curvature, something that's barely curving, well then K is low. Well, that means 1 over R is low. Well, that means R must be high. Well, sure, because here that's such a wide open curve that the tangent line, oops, I guess I'll use red here, that the circle that has that tangent line must be huge, which I'm not even going to try to draw the whole thing. It would be massive. So that's what you're saying when you're talking about curvature. It's, okay, if this part of my curve was part of a circle, how big would that circle be? Oh, it's part of a tiny little circle. Oh, then it's got really high curvature. Oh, it would be part of a massive circle. Oh, then it's got very low curvature. That's a physical intuition as to what these numbers quantify. Finally, we end our section on a theorem, which will rewrite a statement that we had previously. In a previous section, we had a theorem that stated that the acceleration vector lies on the same plane is a linear combination of a normal, principal normal unit vector and the tangent unit vector. In this last theorem for this section, we'll see that that can also be rewritten to include the curvature. So, theorem. Let's begin with a vector-valued function. Let R of t be a position vector for a smooth curve C. Let's have t of t be the normal tangent vector and n be the principal unit normal vector. The acceleration vector A, which we can say A of t, is given by the second derivative with respect to t of s times t plus the curvature times the derivative of s, the arc length, with respect to t, quantity squared, times the unit normal vector, our principal unit normal vector. Where, and I guess I'll state that explicitly, where k is the curvature of C, and ds dt is the change of speed over time. Sorry, I've stated that badly. That would be the change of the, right, that would be change of speed over time. That would just be the speed. It would be the change in arc length over time. So how much of this arc length have I taken in 1 minute? Oh, that's my speed. So where k is the curvature of c and ds dt is speed. Right, it wouldn't be the change of speed, it would just be the speed. The change in the arc length over time is the speed. All right, so the proof of this, we begin with the result from a previous theorem that states that the acceleration function is equal to the acceleration function, the tangential component, I'm mispronouncing that, the statement from a previous theorem that says that the acceleration vector exists as the linear combinations of the unit tangent vector and the principal unit normal vector, where the coefficients for those are a sub t and a sub n respectively. So here that's the tangential component of acceleration times the unit tangent vector plus the normal component of acceleration times the principal unit normal vector, which we saw was the derivative with respect to t of velocity, that was the tangential component of acceleration, plus the magnitude of v times the magnitude of t prime times n, which was this part right here was the normal component of acceleration. Okay. But now this is the derivative of, well, this right here, isn't this speed? That's the change in, that's the velocity. The magnitude of the velocity is defined as speed. So here this is the change in the speed. Oh, okay, so it's the derivative of this thing. So this would be d dt of ds dt. After all, both of these mean speed. Times our unit tangent vector, plus, now we saw in a theorem earlier in this section that curvature is equal to the magnitude of t prime over the magnitude of r prime. All right, so let's go ahead and state that over here. Recall, curvature is equal to the magnitude of t prime over the magnitude of r prime. Or I could always multiply this over to the other side, which is the magnitude of t prime is equal to k times the magnitude of r prime. Oh, so that means this magnitude of t prime can be replaced with this stuff. So that'll be plus the magnitude of v times k times the magnitude of r prime of t. Like that. Oh, but, there you go. R of t is a position vector, which means that the derivative of the position vector, that's the velocity vector. Oh, okay, so really this is just v magnitude, and that's another v magnitude. Okay. Oh, but we just saw that v's magnitude is the speed. So here, this one is speed, and so is that one. So we could write this as d dt of ds dt times t plus, here that one is also ds dt, and that's also ds dt because that's what we're defining as a speed using this parameter. So that's going to be ds dt times ds dt times our curvature. Oh, but now that's just the second derivative, because that's already a derivative with respect to t, and that's another derivative with respect to t. So we can write this as d squared s dt squared of t plus, and here that's the derivative times the derivative again. Well, that's the derivative squared. That's going to be the speed squared. ds dt squared times the curvature. Oh, and I'm forgetting my n here, aren't I? Which is our result. We're looking for the second derivative of s with respect to t times t plus the curvature times the speed squared times the principal unit normal vector. And that's our result. Note that this does not give us anything new. It still gives us that the acceleration vector is a linear combination of the unit tangent vector and the principal unit normal vector. All that changes is the representation of how we can find the tangential component and the normal component. This would give us the same answer. It's just here you can find it by using the magnitudes of t prime and v, or you can use it find it using speed and curvature. Right? It's just a different way of accessing the same information. And that brings us to the end of our section. So that is everything for this topic. If anybody has any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.